Hi, it's Mr. Anderson, and this is Chemistry Essentials video 44. It's on catalysts. Catalysts can speed up a reaction, but they're not consumed in the reaction. One of the greatest chemistry demonstrations is elephant toothpaste. And I'm going to put a link right here to a video. This is from Brian Swarthout, a friend of mine, and his son Sam is doing the elephant toothpaste demonstration. Essentially, you add a catalyst to it, and then you have this reaction go really, really quickly. And so please give that a watch. Brian makes some wonderful videos in chemistry and physics. I'll put a link to some of his stuff down below. But how do catalysts work? Well, essentially they speed up a reaction. Some catalysts will actually slow down reactions, but in general they're going to speed it up by lowering the activation energy, the amount of energy we have to put in a system before we can stress those bonds, break them, and form new bonds. And so it has to go through this transition state, but a catalyst can stabilize that transition state, and therefore it can lower the activation energy and it can speed that reaction up. Now, some catalysts will actually add new intermediates. In other words, they're going to add new steps in this overall reaction mechanism. And so if we look at the energy profile of a reaction, remember we've got reactants on one side and products on the other. This would be an exothermic or an exergonic reaction. And so essentially we've got reactants, we've got products, but if we want to move between the two, we have to add a little bit of stress to those bonds. In other words, we have to achieve this transitional state. Eventually we can break those bonds and we can form new bonds. And so let me show you a catalyst at work. This is catalase, which is an enzyme found in almost all living cells. So what I'm doing is adding a little bit of hydrogen peroxide to a bag that's got yeast in it, and you could try this at home. Shake it up a little bit and you can see I'm producing a huge amount of oxygen gas right there. And so hydrogen peroxide would do this on its own, but if we add an enzyme to it, we can speed that whole process along. So how does it do that? If we look at the reactants on the left, that's going to be hydrogen peroxide, and the water and oxygen on the right, we see that we have to get through a large activation energy. And so what does catalase do? Well, scientists think there's a heme group in the middle of it, and that means just it's a number of atoms, but it's got iron right in the middle. And what that iron's acting to do is to pull one of those oxygens away. So it's stressing that bond on the hydrogen peroxide, and it's stabilizing this transition state, so it's more likely to fall into that just water and oxygen. Again, it's going to release energy, but if we look at the energy here, and if we look at the energy here, the net amount of energy that we're getting out is going to be the same. That catalyst is just acting to lower the activation energy. Now, sometimes it works by creating new intermediates and new steps in the reaction. And so in this elephant toothpaste experiment, you're taking concentrated hydrogen peroxide and soap, and then we're adding potassium iodide to that, and that's simply going to act as the catalyst. Now, what's it doing? That iodine is going to grab one of the oxygens, so it's going to make this intermediate, which will then bond with the other hydrogen peroxide, and that's going to create water and oxygen. And so we're really breaking a one-step reaction into two steps, and then we've got a new intermediate here. Well, what does that look like on an energy profile? This would be our original energy profile. We got reactants on one side, products on the other. But if we look at this two-step process, what we're doing is we're actually lowering the overall activation energy by doing two steps. In the first step, we're freeing up that oxygen, then we're bonding it to the other hydrogen peroxide to make water. And so we've lowered the overall activation energy of that reaction. And so did you learn to translate energy profiles? That's what this is right here. Particulate representations, and then even symbolic representations for chemical reactions with and without a catalyst. I hope you did, and I hope that was helpful.